Hi everyone! This video is intended to help you get an idea of what we as coordinators look for during the teaching section of the interview. It is divided into two segments. During the first section, Dawson will demonstrate several common teaching errors. I will stop the video after each distinct error to point it out. During the second section, RJ will teach the same section problem in full, showing you what we consider to be a very good execution of that same problem. Before we begin with Dawson's segment, I'd like to mention one error that is too broad to be called out specifically. The problem of lecturing too much. Throughout this first segment, Dawson will not have much interaction with his sectionees. Students learn better when they are actively involved in creating the solution to a problem. It's why we have sections in addition to lecture. Keep this in mind as you watch Dawson teach. Both Dawson and RJ will be teaching the weights and balances problem that many of you may remember from sections you've had previously. Let's start now with Dawson.
Hi everyone, welcome to section. So today we're going to be talking about recursion, and the problem that we're going to be solving today is a balancing weights problem. So the basic question is we have a scale that's a balance scale, which means it has two sides that either are in balance or out of balance. And what we want to do is we want to measure some target weight. Let's say the weight is 3 pounds. What we do have is a list of smaller weights that we can use to sort of try to balance that target weight. So for example, if I had a 3 pound weight, then I could put a 1 pound weight on the other side and a 2 pound weight on the other side, and then they balance out, and I'd say, yeah, I can measure that. And so what I want to do is write a function that basically, given the target weight and a bunch of smaller weights, says yes or no, is this target weight measurable? Right, does that make sense to everyone? You guys have questions so far? Cool. All right, let's actually solve this problem. So the way it looks is sort of as I explained. We have a function that returns true or false, and it's called isMeasurable. And what I want to take in is, first of all, an array of weights, which is those smaller weights that I'm trying to use to balance my target weight, and then a target weight, which is also just an integer. And then let's say anti-num weights, just because we need to know how big our weights array is. Okay. So since this is recursion, obviously we're going to have some sort of base case to start off with. So in the balancing weights example, what's our base case?
No real student will know the answer to that question. I'm sure some of you did not familiarize yourself with the problem before watching the video. Did you know off the top of your head what answer he wanted? Dawson explained the problem, but he did not supplement it with diagrams or pseudocode. Even if his verbal explanation was excellent, students need some written reminder of that explanation, or they will get lost. Dawson made the mistake of jumping into code too early. He should have written down examples to solidify the student's understanding, drawn a diagram, and broken down the problem into a high-level algorithm. Let's see what happens when he tries that approach.
Hi everybody, welcome back to section. So the problem that we're going to be talking about today has to do with recursion, and specifically it's about measuring weights. But before we jump into that, I want to make sure that you guys really understand recursion. So do you guys feel comfortable with the Fibonacci example that Jerry's talked about in class? I'm just going to go over it a little bit here just to make sure that we're all okay on the same page with recursion. So the Fibonacci problem is basically, we have this Fibonacci function which takes in some integer n, and it returns us the nth Fibonacci number in the sequence. So, maybe the sequence is 0, 1, 1, 2, 3, 5, and so if this is n is 0, 1, 2, 3, 4, 5. Okay? And so given this n, we want to return that Fibonacci number. And the basic idea is that we have this a simple case where we know that if n is 0, then we can return 0, and if n is 1, then we can return 1. And otherwise, Fibonacci is just the sum of the previous two Fibonacci numbers. And so we can actually reframe that recursively by saying, well, if n is not 0 or 1, then we can just say return the Fibonacci number for n minus 1 plus the Fibonacci number for n minus 2. And that is recursion. Any questions about Fibonacci?
Dawson started off this section with a simple recursive problem, Fibonacci. It's a nice idea, but ultimately not helpful for students. Problems like factorial and Fibonacci are useful initial introductions to what recursion is as a concept, but they are so simple that they fail to add any understanding to more complicated recursive problems. However, Dawson's concept is good. It is a great idea to simplify the problem that you teach. But that should take the form of a simplified version of your current problem, taking care to make it directly relevant to your final solution.
All right, cool. Let's get started on weights then. So the problem that we're doing with weights is we want to measure some target weight using a balanced scale. And specifically the question we're trying to ask is, let's say we have a balanced scale which can tell us if two sides are balanced. And we have some target weight like 3 pounds that we want to measure. We also have a list of smaller weights that we can use to try to balance the scale in order to measure that target weight. So maybe if we have 1 and 2 in our list of smaller weights, we can put the 3 on one side and the 1 and 2 on the other side. So let me just draw a diagram to show you what this kind of looks like. We just have two sides. It doesn't tell us how heavy whatever we put on it is, but it tells us if they're balanced. So we could put like a 3 here and a 1 and a 2 here, and that would balance out. Okay? And so the idea behind this for recursion is we want to basically say, given this list of weights, right, we can actually put these weights in multiple different locations. Like we could say, let's say my list of weights is 1, 2, 4, 7. For each of these weights, I could put it on the left side, or I could put it on the right side, or I could, leave them out altogether. Like for example, if I didn't have the 2 and I wanted to measure the 3, I could actually still do that. I just have to put the 1 on the left side and the 4 on the right side. Right? So the reason why recursion actually kicks in here is because we want to try out every single possible arrangement. We want to say, for each of these small weights, I want to try, to see if it's measurable if I put it on the left side, and then if I put it on the right side, and then if I don't put it anywhere at all. So in that sense, if we're doing this problem, then we could basically model recursion like this. We could say 3 is our initial target. We could try putting it on the left side, so it's now it's 4, or we could put it in the middle, or we could leave it out, which would make it 3, or we could put it on the right side, which would make it 2. And likewise with 4, if we're measuring our next bit is 4, then if we put it on the left side, this is 8. If we leave it out, this is still 4. If we put it on the right side, it's 0. And we can do the same thing for all the other cases. So this is 7, -1, or sorry, 7, 3, -1, and so on. And obviously, -1 doesn't really isn't an actual physical weight, but we're saying that basically just means that the right side is heavier than the left side. And so, if you notice, we hit the 0, that means that we actually have a measurable situation. We have the 1 on the left side, the 4 on the right side, and they happen to balance out. So we can think of target as the difference in weight between our left and our right sides.
Dawson used an example and made a diagram, which is great. However, his diagram was not very good. Notice the top of the diagram, which consists of a 3 with lines to a 4, a 3, and a 2. If you were a sectionee who dozed off, how would you know what was going on? What is Dawson adding? What line represents what? Which weights are left? Dawson left a lot of important information off his diagram. At each level, he included the current target, but he should have also included the list of weights left, as well as an annotation on each edge that said which weight was added and where it was added. A good rule of thumb is that if a person walks in the room after you leave and your diagram is left on the board, that person should be able to tell what you were doing in the problem.
Okay, so this is basically how the recursive structure works. And now we're going to actually just jump into code to sort of explain, how does this actually get written in code. Okay, so erase this out of the way.
Here's another mistake. Dawson erased his diagram. In an ideal world, you would never erase anything. Students need to be able to refer to the conceptual work that they've done while writing the actual code. Erasing should only be done as a last resort when there is absolutely no board space left. If you absolutely must erase something, you do not want to erase the diagram, one of the most important parts of the lesson. If Dawson had actually run out of room, he should have erased his factorial problem.
So the function that we're writing is called isMeasurable, and it should return true if our target weight is actually measurable by balancing smaller weights on the scale. So it's going to be a Boolean function called isMeasurable, and it returns true or false. And what we're going to take in is a bunch of things. For example, we need those actual weights themselves, so it's going to be an array of weights, or an array of integers called weights. And we also have the target weight that we're trying to balance out. So in the example that I just showed, 3. So that's going to be int target. And then finally, because we have this as an array of integers, we need to actually know the size of that array. So I'm going to write that down here as num weights. Okay.
Dawson made a mistake when beginning to write the problem. He started writing the prototype halfway down the board and a third of the way over. He therefore ran out of room, making his solution cramped and hard to read. As you will see later in the video, he will be forced to move half his solution to a different board. This is something you want to avoid. Always start your writing at the top left corner of the board.
And so to start with, we have some pretty simple cases, right? Whenever we're talking about recursion, we want to solve the easiest problem to solve as our base cases. So for example, if I told you to balance me if I asked you if you could balance a target weight which was nothing at all, that weighed 0 and maybe the weight just doesn't exist, then your answer would be yes, I can balance that by not doing anything, right? So if target is 0, then essentially I can say I can return true. Right. And actually, this turns out this is going to be useful for us later, because if we think about target as not an actual weight, but the difference in weight between the two sides, then as soon as the difference is 0, we're balanced, so we're done. Okay. And likewise, the other way we can think about this, the simple case is if num weights is 0, if I don't have any weights that I can measure with, then obviously I can't balance anything out. So if num weights is 0, I can return false. And that basically says, once I'm out of weights, I can return false. And the thing to realize here is that we're actually going to take advantage of this variable num weights. What we're going to do is we're going to say, maybe this starts out as an array of 5 different weights, but every time we use a weight, we'll just pick off the one from the back and say, now we have 4 weights left, and now we have 3 weights left, and so on and so forth. So as soon as it hits 0, that means we've tried using all of our weights, and at this point, we still haven't been able to balance the scales. Okay. So
Could we also do that with an index where we keep track of we started the first weight and we kind of increment that index until we've gone through all the weights?
Yeah, I don't know, that kind of makes a little more sense to me.
Yeah, because it kind of starts at the beginning. It's kind of weird, ripping things off the end. It seems like it makes more sense to start at the beginning.
So you guys, I guess you mean passing another index variable. We could do that. We're just going to do it this way because this is actually the way the solution has it, and it's you don't have to pass in that other variable parameter. So we're going to do it with this num weights and go from the back instead, because this works.
Here, Dawson did not go with a student's suggestion that was perfectly correct and probably more intuitive for most people. Instead, he taught the solution, simply because that was what was on the paper he was given. Students will understand the problem better if it is their code, not yours or the lecturer's. You should not force a specific solution on your students if the version that they find to be more intuitive works perfectly well. Of course, you don't want to let them go too far down the wrong path. This is where preparation comes in handy. You need to be aware of the various ways of solving the problem and be open to student suggestions if they're reasonable.
Okay, so what we want to do at this point is, these are the base cases, and we want to go into the more, let's say it's not either of those cases, so it's a little bit harder to solve this problem. Then what we want to do is, if you remember back from the diagram, I had this setup where, given this problem, I can split it into 3 different subproblems, where I say either the next weight is going to go on the left, or the middle, or the right. Okay, so I'm going to try out all 3 of those. So I'm going to start by getting the next weight and storing it in here, next weight. And, like I said, it's going to be the last thing in the array. So it's just going to be weights, bracket. And so does anyone know here what index I would use? If I want to get, if my num weights, my weights vector is num weights large, and I want to get the last thing. Oh. Okay, so it's okay. It is num weights minus 1, because arrays are 0 indexed in C++, or in Java, or lots of languages. Okay.
Dawson just answered his own question, which you never want to do. Sometimes it takes a little bit of time for people to respond, and you should be prepared to wait it out until someone says something. By answering your own question, you teach your students that they don't need to participate, because you will answer the questions for them. You need to be the least awkward person in the room. If you wait it out, I guarantee you someone will feel the need to fill the silence. If you don't wait it out, you will never get good student participation.
So I pull out the next weight, and I want to see what happens if I put it on the left side, what happens if I put it on the middle, what happens if I put it on the right side. And so I'm going to have basically 3 different cases. So here, I'm a little out of room, so what I'm going to do is I'm going to move over to this board. And let's say the next line is going to go here. Okay? So what I want to do is store, figure out my new target weights for the recursive calls, because if I try this next weight by putting it on the left side versus the right side or leaving it out, then I have 3 different scenarios, right? So the first thing I want to do is I want to calculate the actual weight, how target is going to change. So what do you guys want to call that variable? If I try the weight on the left side, what do we want to call that new target?
Left target?
Left? Yeah, left target? Okay, perfect. That's a great answer, Lynn. So left target equals target plus next weight. Okay, and remember this is plus next weight because we are increasing the difference in the weight and making the left side heavier. Right? And how about in the middle? If we don't use this weight at all, what do we want to call it?
Left middle target?
Yeah, we could call it middle target, and we could actually just use target because it doesn't change at all. It's like plus 0, right? So we're just not gonna make a variable for it at all. And how about on the right side?
We've said several times in this video that we want student participation, but be mindful about the type of participation that you encourage. Interaction like the example we just saw is not very meaningful. It is easy to hide the fact that you have no real interaction by asking trivial questions like what to name a variable or how to increment a counter in a loop. Be sure to choose questions that make the students think. That's all we have from Dawson. Now we have RJ, who is going to teach the same problem to the best of his ability. That doesn't mean that this is a perfect section. I'm sure you will find plenty of things that could be improved. However, by our standards, this is a very good teaching of this problem, and it is a great model for you to base your teaching off of.
So welcome to section, guys. We're going to be talking about a particular problem regarding recursion and measuring weights this week. So I'm going to give a quick overview of what the problem is. Feel free to interrupt me, stop me if you've got any questions along the way. Once we've done that, we'll kind of map out some pseudocode, and then we'll go into writing the actual code for the solution. Sound good? Awesome. Cool stuff. So the problem we're dealing with this week is basically what's referred to as old-fashioned measuring. So you guys might have remembered, like, back in elementary school, you had these, like, balance scale things, right? You had, like, the 2 buckets on each side, and you could put, certain weights in one side, and you had different sizes, like maybe 1, 5, 10, and based on the number of weights and the values of the weights that you put in, you can create different total values, right? And what's neat about this is you can use it to, measure arbitrary amounts, right? So, like, let's say we've got some, like, question mark blob. We don't know how much that blob weighs. We just put it on the right side of the scale. On the left side of the scale, we add the 2 weights, and we can see, hey, if this scale is going to balance, this is going to weigh 13. Does this make sense to everybody so far? Sweet, awesome. Now, let's say, like, you're sort of strapped for cash, right? And you've got this balance measuring scale, but, maybe you've only got 2 weights, right? And let's say, for the sake of continuing this example, we've got the 3 and the 10. But we want to measure some other new weight. And we know that this other weight isn't 13, right? So immediately you kind of look at this and you'd say, like, hey, we can't measure that, right? It's totally impossible because we only have a 3 and a 10. We could maybe measure it if it were 3 by putting 1 there. We could maybe measure it if it were 10. Let's look into the future and pretend that we know that this is 7, right? Can't measure 7 with 3 and 10, right? That's impossible. Or is it? Any of you guys see a way that we could, potentially confirm that this is weighing 7 with just the weights 3 and 10?
If you put the 10 on the left and the 3 on the right.
Okay, awesome. So Patrick has hit the nail on the head here, right? What we can do is we can basically add weights to either side. And we can say, well, if we add 3 to 7, that equals 10. So that should balance out with the 10 weight on the other side. Does that make sense, everyone? Sweet, awesome. So what's really neat is this translates super beautifully into a recursive backtracking, or excuse me, a recursive problem. I'll go ahead and write the prototype up here just so that we know what we're trying to solve. We won't write any code yet. So we want to write this function bool is measurable. And this is going to take a few things. It's going to take an int array weights, and it's going to take an int target that we want to measure to. So for this particular example, maybe we wanted to weigh 7, and we'd pass in the weights 3 and 10 is measurable should return true. If, for instance, we had the weights 4 and 10, could you guys think of a way that we could measure that with 7? Yeah, probably not, right? There's no way to kind of divvy those out. So that's a bit of a bummer. But this is what we want to do with this problem and this approach, basically figuring out whether we can measure this unknown target. Everybody following so far? Awesome. Okay, so before we dive into code, let's talk about this approach from kind of a high level. I mentioned recursion might be a good strategy for solving this problem. Any of you guys know why recursion might be a neat approach here?
Well, I mean, if you put like a weight on one of the sides, maybe, then you just sort of like have sort of a similar problem because you've got a bunch of weights left and you still have to make that same decision.
So let's say like we make the decision to put the 3 on the side with the 7, right? How is that sort of a simpler version of the problem we had before? What are we now is measurable in? So if we've added the 3 to the 7, what's our new sort of target on this side?
10?
10, cool, right? So, at this point now we're saying like, oh, we were trying to measure 7, we've made some sort of choice to say like, oh, we're gonna put the 3 on this side, and now we're trying to measure 10. If, for the sake of argument, let's say we took 3 and we put it over on this side, what would our new target to measure be?
4?
Okay, awesome. Yeah, so those are sort of our 2 recursive cases here, right? Now, with any good recursive function, we also have to have a base case, right? So what do you guys think might be a base case here?
If we run out of weights.
Okay, how would we know if we've run out of weights?
If we've tried them all.
Okay, so we can say run out of weights. And what's that going to be in terms of our result?
False.
Yeah, so that's false. Just put that as an F. And we already said that our recursive cases were adding to the left and adding to the right. Great. Okay, so we've got our sort of false recursive base case. We have no more weights left. How do we know that something is measurable or we want to return true from this function? Is that another base case that you guys might be able to see here?
If the left and the right sides are the same weight.
Okay, cool. So if we continue with this approach of adding weights to each side and sort of modifying the target, what would the target get modified to so that we hit that base case when we know that they're the same weight?
0?
Cool, awesome. So if target's 0, then we're going to return false. Or excuse me, true. Don't want to return false on that. Okay. This seems pretty good. Are you guys following this kind of pseudocode approach? This is like one of the really neat things I think about recursion is that you can solve these otherwise challenging problems in just sort of a very concise, expressive way. You'll see when we actually get to the code here, it's not that much at all. Really neat with some of the stuff you can do here. Okie dokie. Let's see if we can kind of take some of this code pseudocode and translate it into actual code over here. So do you guys want to deal with the base case first or the recursive case first? Which one seems a little bit more natural to do?
The base case?
Base case? Okay, cool. So how do we know if we've run out of weights?
I guess when we do the recursion, are we gonna shrink the size of the array? So.
Okay, so you guys will remember we're in C++ land here, right? So do we even know how long this array is?
We could use length to get the length?
Yeah, sadly we don't have length, and I think this actually highlights a potential typo that I have here. In our prototype, we need the number of weights, right? So you guys will recall that we don't know how many elements are in that array, so we'll have to add that in our function prototype. I think I may have translated that incorrectly from the assignment handout. My apologies. Great. So if we know the number of weights, it's pretty easy to tell if we've run out of weights, right? What's our base case there?
If number of weights is 0?
Cool, great. So that'll just be if n weights equals 0, we'll go ahead and return false. Okay, fantastic. How about our success case? Hopefully this one's pretty straightforward as well, right?
If target is 0, return true.
Cool. You guys will probably find that when you're writing your own recursive functions, hopefully you can kind of get these short, succinct base cases, because I think it makes everything else a little bit easier to follow and it's very clear what you're doing. Okay, great. How about the recursive cases? Because these get a little bit trickier.
So I guess if we're adding it to the right, so like with the 7, we added the 3 and it became 10. So I guess when we add to the right, we increase the target.
Okay, cool. So basically we're modifying the target.
Mm-hmm.
Any other parameters that we need to change?
Shrink the number of weights.
Yeah, okay. Given sort of our approach here, what would be a good way that we could accomplish that? We've just got this raw C++ array. Any suggestions on how we can shrink an array?
Could we just pretend that there's less elements?
Okay, how could we do that?
Just change n weights to be n weights minus 1.
Okay, so we could do that. If we're doing that, which weight do we need to deal with in the array each time?
The last one?
The last one, right? Because that way we're basically saying, we're just going to chop these guys off the end, and the same value that we're passing in for weights is just going to be the same one each time. Does that make sense? That's a little tricky on the pointer stuff. Lynn, are you following along with that? Great, awesome. Okay, so let's go ahead and write our recursive call. So this is going to look like is measurable. And we said we wanted to keep weights exactly the same. What's the parameter that we would pass in to target if we add to the left?
So I guess if we're adding to the left, we're shrinking the target, so we target minus n weights at.
Great, yeah. As we can see from this example, when we put 3 on the left, our target, which was 7, now became 4. So target minus weights of, and you know what, let's draw this guy down in the next line here, a little easier to read. Weights of n weights minus 1. And then what do we pass in for n weights?
N weights minus 1.
Cool, awesome. Okay. So there's our recursive call to adding it to the left. What are we going to do with the result of this recursive call?
Can we just return it?
Okay, so we could return it. Do you guys think that would work okay?
Yeah, well, if it's true, you want to return it.
Okay, great. So Lynn is kind of on the right track here. with if this is true, we do want to return that. However, if this is false, we still want to make sure that we make that other recursive call for adding to the right in addition to that. Does that sort of make sense, Patrick, why we need to have the two recursive calls?
Mm-hmm.
Sweet, awesome, yeah. Because you guys will find this in a lot of your recursive algorithms. There's sort of this common pattern of, hey, if my recursive call succeeds, return true. Otherwise, we're going to return false. Otherwise we're going to keep going through until we've tried all the potential recursive calls, and then we're going to return false. So we can probably put this in like some big old if statement to only return true. And we said if this recursive call works out, then we're going to return true. Does that make sense? Everyone? Great. So I'll leave some ominous white space here. Okay. So as you guys may know by now, this white space is sort of a good hint that maybe we want to leave something in here. We still need to do this add to right trick. Can anybody see a way that we can kind of couple that into this if statement here?
Could we just say like or?
Great. Yeah. You can kind of think about it the other way around. When do we want to return true? Well, if this is true, or the add to right case is true. Awesome. So we'll go ahead and or that in. Is measurable. And we'll basically make the same recursive calls, but slightly different. So instead of target minus weights, we're going to do target plus weights, right? This is n weights plus 1, minus 1. Okay. I think I got all my parentheses right. Okay. So if those two things are true, we're going to return true. Afterwards, we can just return false, right? Are there any other recursive cases we need to consider? No, we're good. Okay. So this is looking pretty good. Anybody see any cases that this function might not handle, or does this seem robust to everyone?
Seems okay to me.
Looking good? Patrick, you see any problems? Okay. So what if, I said, I want you guys to measure 10 as the mystery weight, right? So 10 is going to be the mystery weight that we want to measure over here on the side. And we'll say for the sake of argument again that we've got 3 and 10 as our two weights. What's our function as we wrote it right now going to return? Should return true, right? We've got a 10 weight. Anybody see a reason why it might not?
I guess if we use the 3 weight first, then we always have to add or subtract the 3 weight before we get to the 10 weight.
Cool, right? So Lynn hit the nail on the head here. If our vector looks like our array looks like 3, 10 in terms of the weights that we've got, our recursive call is saying, hey, add this weight to the left or add it to the right. And that means our two recursive calls, if our target is 10, are going to be 7 and 13, right? And obviously neither of those are going to get matched up with 10 to reach a target of 0. Okay, so we've got a bit of an issue here. Can anybody think of an easy way that we might be able to fix it?
Well, we could have a third recursive case and just don't change target.
Cool, awesome. Yeah, that's perfect, right? What we can see from this example is, well, if we just ignore the 3 weight, the 10 weight is going to work out for us, right? So drop the 3 weight on the floor, forget about it forever, and then our next recursive call, we add 10 to the left, and we're good to go, right? Everything works out. Does that make sense to everybody? Awesome. Okay, so let's go ahead and make a third recursive call. The parameters are going to be a bit different on this one, right? What are we going to pass in for weights?
Weights.
Cool. That doesn't change. What about target?
Just target.
Cool, yeah. We don't need to change that one at all, right? As we said in our example, we're taking that 3 weight and we're just forgetting about it. So there's no need to do anything special here. We can just compute the same target, but here's where the magic happens. What do we pass in for n weights?
Still n weights minus 1?
Okay, awesome, yeah. So we're still disregarding that weight, right? But what we're effectively saying here is since we're not modifying target, the recursive call is basically just chopping that weight off the array. We can't use it anymore. Close up the parentheses there. Okay, cool. Anybody see any other stuff, any other problems, edge cases that this solution may run into? It's looking pretty robust. Cool. Yeah, when you guys actually have a chance to take a look at the assignment handout, you'll notice that there's this kind of pattern that we can actually simplify just a little bit even more. Sometimes in your code you'll have if some condition return true, else return false. But what you can realize is this whole thing is really just a condition, right? So instead of if this, return true, else return false, what's a way we might be able to simplify that expression?
Just return the expression?
Yeah, so if we wanted to, we could rewrite that. Instead of the if, we could just return that, save ourselves a couple lines of code. This one's already a bit tricky to grok just because there's so much happening on here. So definitely okay if you guys need to expand things and write a little bit more to make it clear. Great. Any other questions on this problem? You guys feeling pretty good? Awesome.
Well, that's all we got. Thanks for watching, and good luck at your interview.
Okay, that's all I got.